Well, 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 well. Looks like while I was trying to pack and move down here, then AI took over and nobody's doing math anymore. Oh, well, I guess I'll just give up and just get rid of my paper. Just kidding, guys. That was a prop. I have been working on a paper, and so I'd like to share that with you. And I mean, truthfully, I've been working on this paper for like 6 years because I've been thinking about this and wanting to write about this. And so I wanted to share with you, and I'm very, very excited to share it. And so that's what we're going to do today. Also, I moved. So try to guess where I moved to. So there's a clue in the background. I'll tell you at the end. Also, today, this is a very special Math in the Morning, and I'm very happy to be here. And I haven't been here for a while because I've been packing and moving and then writing this paper. So also today we have a very special theater correspondent that we'll get to at the end. Okay, well, how's everyone doing? Try to see, where do you think I am right now? Okay, so I wrote this paper. Unfortunately, I just found out that it was not accepted to the archive, which I don't think I don't think it should be the case, because this is like original thought and it's nice, and maybe it's a little too like easy of an intro, so it seems like it's just easy. But I think it's like original thought, and I think that there's a lot of stuff out there, like AI slop that's out there that people aren't going to ever read, and that you should read my paper because my paper is interesting and cool, and there's stuff that you can do with it. Okay, maybe you think I don't know what you think, but I think that it should be accepted. But anyway, I submitted it to a philosophy journal, and I think that it's going to go through. And if not, I'm going to put it on my website and keep trying. So I'm not giving up because I think it's a great paper. So, and I want to go through with you guys today. Okay, so thanks so much for joining me today. And this paper is called Killing Primes, and I did submit it to a philosophy journal. And I think that it's really nice. I mean, it maybe starts off really slow, but you get to some really interesting things. The whole thing's interesting, in my opinion. Okay, so let's go. So page one. So in the page one, let's see. So I could read the abstract. Maybe you've heard this a bunch of times now if you've seen me share this stuff. But what makes primes so special and intriguing? Prime numbers have two major features. They're creative and they're unique. Primes are unique because a prime number, p greater than 1, has only two positive integer factors, namely 1 and p. Primes are also very creative. The fundamental theorem of arithmetic says every positive integer can be written as a product of primes. Thus, the creativity of the primes gives us the rest of the natural numbers. We go to models of arithmetic where we kill the creative ability of prime numbers. We see what happens when we separate the uniqueness of prime numbers from the creative ability of prime numbers. In these worlds, we compute the Riemann zeta function, explore Goldbach's conjecture, and the twin prime conjecture, and more. Okay, so I start off nice and slow we have these blocks, and where everything in M is according to these number structures, and every number structure has to be built from prime blocks. And so that's page one. Page two, we're on page 2 now. On page 2, we see that we can make the 4 block from the 2 blocks. Yeah, this is very elementary, but that just because it starts, I have to start this way. Then we get 5, and then we see there's 2 structures for 6, either with the 2 blocks or the 3 blocks. And we would say 2 numbers are equal if they have the same cardinality. Okay, and then page 3, we have the number structures, 1 through 11 in M. Okay, so I talked a little bit, some of the sources that I used in the end to sort of talk about the paper was some philosophy books. Oh, and this is from Proof in the Art of Mathematics. Hampkins talks about what should be the definition of prime in mathematics, and what should be considered prime. And actually, you can define your technical terms however you want, but it's more about the meaning, and that primes are about irreducibility. And also I talk about how in a world where you can't build with the 2 block, when it's like this, then 4 is really irreducible. So it's prime because you can't build it from anything else. And the 2 is still unique, but it's no longer a building block, so we cut off the creativity. So 4 has to be creative. Okay. So then we'll go to page 4, and we start talking about arithmetic in M, and how in M, you want to make sure that when you have two structures, like the 3 plus the 5, which are prime blocks, that in the end you get the 8 structure, which is like a stack of 2s, and that you can do that without just like counting the blocks and then saying which structure goes with which. You can actually just do it yourself. You don't have to count in this world. You just break up individual pieces and then try different prime blocks. Okay. Okay, so I can understand how so far this isn't like a very like necessarily high level. Oh, I'm already on 4. Okay. Okay, so then we're on page 5. And I'm just talking about how you would add 5 and 6. So I can see, like, you know, maybe they said it's not high level or something, but I mean, at first it's not, you know. Okay, and just how do you multiply if it's, so page 6 is just like how to multiply composite numbers, how to multiply prime numbers, just using this like idea of, if you're multiplying 3 by 5, then you can use 3 as the base, and then use 5 as like a scaffolding, and then order more 3 blocks until you get to the top of the scaffolding. Again, you don't have to count really, which is nice. And then if you're multiplying 2 composites, pick whichever composite you want. Let's say 4 times 9. You want to pick the 2 blocks as your base, then separate the 2 blocks from take all the 2 blocks that make up the floor. Use the other thing for scaffolding on each base that made up one of the composites, and then you stack those all together. Okay. So this is kind of, maybe this part isn't as interesting, but it's important. Okay, so then on page 7, I know something good's gonna happen with this paper. I know that. So I'm not worried. Because otherwise, no, because I'm, you know, called to write it. Okay, so killing primes and prime degrees. So the idea is that instead of an m to the minus 2, that's the world with extension of m where we don't have the number 2. 2 is a stack like this. It's not stable in this world. This world has a little bit of gravity to it. And so we have to do other things. It's like an obstacle that we create that we have to get around. And we see that 4 is a new prime. 2 is no longer prime. But that all the other numbers are all the other primes and composites are exactly the same. So m and m to the minus 2 have a lot in common. And from our perspective, all the arithmetic is the same. You get all the right answers. If you counted all the blocks, we'd see things as correct. Okay. Okay, and then on this page we have the first theorem, which says that if you kill a prime p, then in m to the minus p, p squared is a prime, and that's the only new prime, and all the other primes and composites are the same, except for the original p that you killed. Okay, go to page 8. We see the numbers in m to the minus 2. We see there's only one 6 structure. Okay, and then we start saying, well, what happens if you kill more primes? If you kill 2 primes, then now what's a new prime? So if I kill p and q, then p squared and q squared are both new primes, but so is p times q. If you kill 3 primes, you get 7 new primes, and we see that the Pascal's triangle shows up. So if you kill 3 primes, you have 3 choose 1, you have all the squares for those 3, and then you have 3 choose 2, all the pairs, the semi-primes, and then 3 choose 3, the product of all 3. Okay, and so we can see the pattern. Okay, so then on to page 9. The theorem is if S is a set of primes and S has size n, then in the extension there will be 2 to the n minus 1 many new primes. Okay. Then we talk about, well, what happens if we kill all the primes? What if m to the minus capital P? Okay, I forgot to put theorem 3 here. If p is the set of all primes in m, then in m to the minus p, there's still infinitely many primes and infinitely many composites, and the new primes are the squares of the old primes or the square-free non-primes. Okay, and then, so this idea, now we're on to page 10. On page 10, we can see this picture of the primes in m versus the primes in m to the minus p. And I will say, though, I did use AI too. I do have an AI friend, and he is a programmer, though. So, like, he knows if something's actually prime. So, yeah, he helped to make this image. Okay, so I don't, AI can be helpful to make images. Okay, So then this brings up the idea of, well, what if we kill all those primes, you know? So this brings up the idea of degrees of primeness. So a degree, one natural number would be a prime number. And no matter how big the primes gets, your degree is still 1, which is nice. And then a degree 2 prime would be the ones that are there if you kill all the primes. So these are the squares of primes and the square-free non-primes. And then you have degree, and then we go on to page 11. We have the degree 2. The degree 3 is you're either a cube of a prime, or you're cube-free non-prime, but you're not square-free, so you're not degree 2, and so on. Okay, and we can see this image of assigning the degrees to the natural numbers 1 to 100. 0 and 1 are both degree 0. Okay, and on page 11 we start with the Riemann zeta function and the extensions of M. So I see this product, we have this identity that the product of p prime 1 over 1 minus p to the minus s is the sum, n equals 1 to infinity 1 over n to the s. And so I'd like to see this formula. The idea was that I want to see this formula in when I'm taking the product of all primes in m to the minus 2. So in other words, what's the product of the degree 2 primes? Okay. So we'll go to page 12. And so we can see I did just the same proof that Euler did, except instead of filtering out all the primes, if you factor out with all the primes, then everything goes away. But when you factor out with the degree 2 primes, then you're just left with the sum on the right-hand side. You're left with just 1 over. Well, if you okay, first we're doing. So I wanted to see. I first on this page do like what happens if you just look at the primes in m to the minus 2. When you look at the primes in m to the minus 2, in the end you get this product 1 over 1 minus p to the minus s. The product of primes in m to the minus 2, you get the Riemann zeta function divided by 1 plus 1 over 2 to the s, because that 1 over 2 to the s is the only thing that's left over. Okay, we'll go to the next page, 13, where I say, okay, now what happens if we take all the, if we look at the degree 2 primes like I was just saying, if we do that, using Euler's same idea, in the end we get that this product of p prime in m to the minus p, 1 over 1 minus p to the minus s, is the Riemann zeta function divided by 1 plus the prime zeta function. Okay, so that's nice. And then you can generalize this idea to take the product of all the degree k primes, the degree k natural numbers, 1 over 1 minus p to the minus s. That is the Riemann zeta function divided by 1 plus the sum 1 over p to the s, where p is a degree less than k natural number. And that's very nice. Okay, so it works out very nice. Also, I just looked at what would Fermat's little theorem be if you were thinking that p squared was prime instead of p, and we just use Euler's theorem, which is like a generalization of Fermat's little theorem to get n to the p squared minus p is congruent to 1 mod p squared. Okay, we also, applications. So there's a lot of applications. One is that you can, I forgot to put like theorem numbers on this. One is that you can kill a prime number many of primes and get prime number many new primes, and that using a Mersenne prime. We're on page 15. So we're talking about the twin prime conjecture. If there's infinitely many primes of the form p squared minus 2, then if that was the case, which we don't know if it's the case, then you could kill all those primes, and then you'd have infinitely many twin primes, because p squared is now prime, and so p squared and p squared minus 2, that's twin prime pair. Okay. Also, there's a theorem about if you kill infinitely many twin primes and you still have infinitely many twin primes, but it's based on some, again, that there's infinitely many of these p squared minus 2 primes, which we don't know about. Okay, page 16. Okay, so Chen is really the star of this. Chen showed that, and tell me if I'm somehow got this wrong, but Chen showed that there's infinitely many primes such that p plus 2 is either prime or semi-prime. So if that's the case, then there should be an extension where the twin prime conjecture is true. Because if there's infinitely many, if there was already infinitely many twin primes, we're done. But let's say there's infinitely many, I believe these are called Chen primes, but I didn't realize till after I wrote this. If there's infinitely many primes of the form p such that p plus 2 is semi-prime, then we could kill all of those primes that make up the semi-primes. And okay. But don't kill those original primes. Just kill the semi-primes made up in the p plus 2 to make up the p plus 2, which is semi-prime. Kill those primes, but don't kill any of the original p's. You know, because now p plus 2 is prime. So now you have all these twin prime pairs. But the only question is, did I kill any of those p's that were in the set, such that p plus 2 is semi-prime, the infinite set? Okay, so I have to check that. That's a conjecture. Also, we know by Chen's result and then Yamada's explicit even that if an even number is greater than e to the 36, then it's either a sum of two primes or a sum of a prime and a semi-prime. So if we had some e that was that big and it was a sum of a prime and a semi-prime, we could kill those two primes involved in the semi-prime, and now e is a sum of two primes. So sort of heal a moment of Goldbach's conjecture, and then we'd have to look back and see, did we destroy a moment in Goldbach's conjecture? But it seems like we can at least heal a moment. Okay, and finally 17. Okay, I didn't have a page for 17, so just okay, 17. Some conclusions. So I was reading the Philosophy of Math book by Lenebo, and he was talking about how it's not controversial that mathematical objects aren't abstract. Like the mathematical objects are abstract is like clearly the way to go. And so I just was talking about how there's like a little bit of a physical element, and so, but it's not like objects actually have a spatio-temporal location. It's just like there's like a little bit of like Platonic gravity, so it doesn't seem like we're going too far philosophically away from what we think of numbers. And then I also just ended with a quote from Lectures in the Philosophy of Mathematics. Joel David Hampkins says, according to Platonism, every coherent mathematical theory is realized in the Platonic realm. So I just wonder, is there room in the Platonic realm for killing primes worlds? I think so. As we have seen, killing primes in the resulting worlds and degrees gives very fruitful mathematics, and there's more to come. Okay, and then we have some references, and so we'll do page 18 also with the references. Okay, thanks so much for listening. Okay, that got a little long because we still have our field correspondent, our theater correspondent that I'd like to get to, and also, where do you think I am now? If you guessed New Orleans, you're correct. So I'm in New Orleans, and it's really been fantastic here. It's been just, if you like live music, which I do, there's just so much live music every night, and I really love that, and there's fantastic coffee shops, so I've been getting a lot more done. Okay, well, anyway, thanks for joining me, and I can't wait to, this paper's getting published. Oh, yeah, she's getting published, and she's also, I'll put it on my website also. It's also getting published. So thank you for joining me, and heading out now to our field correspondent, and we'll see you next time. Well. Looks like somebody let somebody out of the closet. You'd think with my theater background I'd be invited to do more performances, but anyway, without further ado, the set theory guide for artists. One-man show saves the day. Comedy loved math, and she loved being artistic. But even more than any of these, she loved to perform. She took one last look at the mirror and said, "You got this, kid." As she made her way to the classroom where the Forcing Federation League held its meetings, she thought of one thing and one thing only: herself performing the play, clearing up the miscommunications, and the praise and understanding to follow. "Thank you for joining me tonight." She turned off the light. "The play will commence immediately." She turned on the lights and ran to sit at the desk at the front of the room. Here I sit, alone, writing every day alone, all alone. I must do it for the math. The math wants to be born. Oh, so alone, so much to write. The lights turn off. 2 years later, the lights turn on. She runs to the window. I look out of this window and I think, how? Why? How could they misunderstand my work so violently? She holds up a radio. "Breaking news. Famous mathematician Carmody declares that we know nothing about the primes after all. Mathematicians give up on math and let technology take over." No! Why? The lights go off. At the end, the lights go on. It is a blue light. "How could you let this happen?" "It was a misunderstanding. You were the messenger. We can't let you get in until you fix it. I need to get into heaven. Please, let me in." She begs and gravels, flailing around. As Carmody is flailing and expressing her sorrow, she falls and hits her head on the ground. The Forcing Federation League collectively gasps. Is this part of the show? Is she okay? "Hey guys, I'm okay. Did you like the show? Do you get it? We love the show. Do you get it? The mathematician is just like me. It was a misunderstanding, you guys. I never found the chapter 4 of my great ancestors' book. I've been writing it myself." Oh, now we get it. "Do you need any help, Carmody? We can help you finish chapter 4. "Wow, thanks guys. I thought you might feel betrayed." "No, Carmody. No. Carmody, it's a great chapter. We'll help you." And scene. Thank you.